Thank you. It's a pleasure to be here with such a distinguished group of scientists and engineers with a common interest in CubeSat technology. Thank you to the Swedish Space Systems, S3. The motto of S3, Space for All, is very dear to us at Morehead. We are a small regional university, and we have had the opportunity to fly a number of space missions quite successfully. And so the philosophy of Space for All is really very important to us. Also would like to thank the Von Karman Institute, in particular Dan Thermal and Padre Testani, who gave a fantastic talk earlier today. Very much enjoyed. I have a few questions for you, don't go anywhere. It's been a fantastic conference for me so far. I've learned a great deal already. The talks especially about detectors, the science detectors, were particularly informative. Some of the talks on the X-ray detectors and gamma ray detectors are relevant to our work at Morehead State in astrophysics research with small satellites, and particularly CubeSats. The Caliste detector, for example, fantastic technology. It's amazing to me that the technology has evolved to the point where we're actually supporting significant science, probably niche science, but still significant science with CubeSats. Incredible. So I'd like to recognize my co-authors here. Bob Twiggs, now at Morehead State. You might have recognized his name, one of the co-inventors of CubeSat. Some other folks from Morehead State University. Dmitry Roldugan is here from the Kaldish Institute of Mathematics in Moscow, and Michael Chennikov also couldn't make it this time. Also have a couple of co-authors from our parent organization, which is Kentucky Space. So to provide some context for my remarks, I thought I would talk a little bit about the sort of state of things relative to small satellites in the U.S. There's been some interesting mentions in early talks about the projected number of small sats that are going to be flown. And it's interesting that I think the previous remarks are very consistent with the research that we've looked at. Projections are an estimated 500 microsats to be launched globally by 2020. There's a reference to the SpaceWorks Enterprise marketing research is where that statistic came from. But the interesting thing for me is that in Kentucky, last year aerospace became the #1 manufactured export. Enjoyed the panel discussion last night because it's a very interesting parallel between the region here and the region of Appalachian, Kentucky that I'm currently in. Terrain's very similar, rolling hills. It's a bit more beautiful here, I must admit, with the Alps in the background. But the terrain's very similar. It's very agrarian, very beautiful. It's sort of horse country. Much like it is here. And I found some interesting parallels from the talk last night, because in the 1960s and 70s, Kentucky was very agriculturally oriented, the economy. In the 80s and 90s, we became more industrial and relied on extractive industries like coal. So basically, we were a tobacco and coal economy through the late 90s. That evolved into industrial-based economics with automotive industry, and just this last year, the aerospace industry in Kentucky overtook the automotive industry. So it's now a $5.6 billion industry in the state of Kentucky. So interesting parallels in the evolution of the economy of the region here and the region that I come from in the southeastern United States. So the increase in the launches of CubeSats is really astounding. Nearly 300% in 2013 over 2012. The cluster launches are making these access to space much more easy for a variety of different customers. Interesting, and just last year, the 2 cluster launches, one from NASA Wallops Flight Facility, launched 29 CubeSats. And less than 48 hours later, which was a record, but less than 48 hours later, the record was broken by Dnepr launch that had 31 small sats out of Yasny. So it's interesting the cluster launches are providing significant access to a wide variety of developers. The first constellation of CubeSats, probably real constellation, was also launched this year. Planet Labs, we have the great fortune of providing mission operations support, and I think they're up to 30 plus satellites now, 30 plus 3-unit CubeSats. And of course, the big news in the U.S. is the Skybox company was recently bought by Google. So there's a lot of activity, and truly we do believe that the next big thing is small. With the contraction in government support for research and the movement of research to the private sector, the CubeSat form factor has become extremely important. So a little bit about Morehead State to provide a bit more specific context. We have quite an outstanding faculty in sort of a remote region. Bob Twiggs, the co-inventor of the CubeSat. We have experienced faculty in RF and communications systems, in ground station equipment, in microfabrication and microassembly. And we do offer a couple of degree programs, an undergraduate degree in space science, which is very science-oriented, and also a master's degree in space systems engineering, which is more engineering-oriented degree. But most of the work that we've done has involved graduate students, and all of the work that we've done has involved undergraduate students. So they're intimately involved in the development of these small satellite systems. So a bit more context, where in the world is Morehead State University? It's in the sort of, we call it the Southeast. Culturally, it's in the Southeast, but it always am surprised by how far north it is in the U.S., but there's a pin dropped in the position of Morehead. Why small satellite research in a remote region? Small university with only about 10,000 students, very science-oriented. So there were we had some resources. We were pretty good in physics and engineering. But I think the primary reason that attracted me there, at least, was the RF environment, the radio frequency interference environment. It's relatively pristine. It's very good at UHF. It's very good at X-band. The noise floor is increasing a little bit at S-band, particularly when the students are on campus with all the wireless devices. Can't be avoided, I suppose. But in the summertime, the students are on S-band. It's pretty good as well. But we're surrounded by mountains on all sides, and we are relatively far removed from any major metropolitan regions, which is good for the RF environment. It's also good for the students because there are less distractions for them from their studies. So it really is a fairly unique environment, and again, very similar here, minus the beautiful Alps in the background. So we've been fortunate to develop a facility devoted just to space research. It's about a $15 million research and development facility that's devoted essentially to small spacecraft development and to astrophysics research that utilizes small spacecraft platforms. We have the great fortune to have a 21-meter space tracking antenna. It's actually a radio telescope and space tracking antenna. It was designed initially as both, but it allows us to provide some mission operations support for a variety of different customers that generates revenue to help support some of our space missions. We're very fortunate to have a class 10,000. We can actually go down to class 1,000 in the clean room if necessary, but generally class 10,000 has been sufficient for the small satellite work that we perform. It's a fairly sizable clean room, and we've been able to build our own satellites there and also support some colleagues' satellite development. In fact, Paraday was there building up EduSat and Unisat 5 for about a year for the Italian Gauss group. So it is a dedicated clean room for small satellite development. Another facility that I wanted to mention because I think it's important from the aspect of making empirical measurements of communication systems is our electromagnetic anechoic chamber. And basically, of course, it mimics the electromagnetic environment of space and supports the testing and characterization of communication systems. One thing that I would like to share in terms of lessons learned is that it's extraordinarily important to characterize your communication systems. In the beginning, we did a fair amount of numerical modeling of antenna systems, but when we build up the spacecraft, the antenna systems and the transceiver systems never actually work like they do in simulation. Very challenging to build antennas, effective antennas on small spacecraft. If you think about the low frequencies, for example, People generally build blade-type antennas, turnstile-type antennas, but the ground plane is extraordinarily small for the low frequencies. And so things just don't work like they do in simulation. So one thing that we've done that has led to some success is to build up what we call an antenna model of the spacecraft. So every spacecraft that we build a flight model, an engineering model, and an antenna model that we refer to. And the antenna model is effectively electrically similar to the flight model, but it allows us to put the system in a chamber and undergo extensive antenna characterization. And we've really come a long way in terms of antenna design. The tuning of the antennas is very different when they're in situ on the spacecraft. You get a lot of unusual reflections with deployables. Patch antennas don't work like they do in simulation on small spacecraft. So it's been extremely important to do the empirical testing and characterization in situ in the chamber. And that's been a fantastic asset to have. So I highly encourage you guys that are, and in fact I see there's a communication session coming up I'm very interested in. But a combination of numerical simulation plus empirical testing, I think, is extremely important to the success of these small sat missions. Our goal at Morehead State is to create the next generation of aerospace workforce for the aerospace industry in the U.S. and the aerospace industry here. We really are not producing aerospace engineers and scientists in the numbers that are needed to support the industry now, much less the growth mode that the industry is fortunately in. But CubeSats are a fantastic mechanism to provide authentic experience for undergraduate researchers. They literally get their hands on spacecraft hardware. When they walk in the door as freshmen, we actually start them learning how to solder and learning how to design schematics. They learn test and measurement equipment. They learn microassembly techniques. They learn some mechanical engineering. We put the sophomores in the machine shop. We do rapid prototyping, 3D printing. They learn CAD design. So it's a very practical approach, and the students get significant hands-on experience in engineering design. In fact, we make them live through design reviews. When we have a flight with, for example, NASA's Launch Services Program, it's not me or our program manager leading the design review. It's generally, believe it or not, an undergraduate student up there for 4 hours providing the lead effort for the design review. Great experience. We make them write reports because that's what we do as engineers, design reviews and reports. So really authentic experience. We also engage in observational astrophysics. In the building we have two groups. We have the Space Systems Engineering group and an astrophysics group, and we specialize in radio astronomy, instrumentation, and also high energy astrophysics, X-ray astronomy, and gamma ray astronomy to a certain extent. And also involve the students in mission operations support. So how do you do this sort of work at a small regional university with limited resources? And really the answer is through partnerships. We have partnerships, excellent partnerships with government, with the NASA, various NASA facilities, with other universities, mostly here in Europe, and with the private sector. So we've in the past partnered with NASA's Jet Propulsion Lab, the Goddard Space Flight Center, the Glenn Space Center in Ohio. We've done some work for the U.S. Department of Defense, DARPA, and Space and Missile Defense Command, who has a tremendous interest in nanosat technologies these days, and some other universities in the U.S., but primarily here in Europe. University of Rome has been a great partner for us, the La Sapienza School, and ultimately the Gauss spin-off group. We've done a number of missions with those guys that have been really interesting and really successful. But lately, because there has been a contraction in government support, we have teamed more and more with aerospace companies. So we've worked with Honeywell Space and Defense Technologies to develop some small satellite computer systems. We've worked with VSEC, a company in Boston that's an MIT spin-off, where we're doing electric propulsion systems, RF ion systems. Actually, they just released an article on an iodine propulsion system that they've developed, and it's literally designed for CubeSats. So those technologies, in my opinion, are going to be game changers. And really enjoyed the propulsion session yesterday, where we taught, where we learned about what's going on in the European research area in electric propulsion systems. So a lot of interesting work here. Other companies that we work with are the Cosmotros, who has provided some launch opportunities for us. And I also should mention the Kalish Institute of Mathematics in Moscow, who is a partner on a couple of projects that we're doing right now. They've been fantastic to partner with. So the importance of the private sector partnership is difficult to understand. It's really allowed us to do a lot more than we have been able to alone. So specifically the missions, and I promise I won't talk about all these today. I'm going to choose a couple that are my favorites. But today we've been really fortunate to launch 5 different satellites. We've done 1 U-CubeSats, 2 U-CubeSats, 3 U-CubeSats haven't launched yet, but we've built a couple under different grants. Some microsat subsystems for a variety of microsats. And last year we launched Bob Twiggs' new invention, the Pocket Cube, which is a fraction of a CubeSat. So I'll tell you a little bit about it. And again, mention some of the ground ops work that we've done toward the end here. But the satellites, just briefly, that we've had the great fortune to launch. KentuckySat 1 there on the top left was our first attempt. It was a 1U, and it was mostly off-the-shelf systems. We were learning. It was a pumpkin kit with a Clyde spaceboard, and we built some transceivers and EPS systems. And it worked fairly well with one problem. It was on NASA's Glory mission, which was on TARS A that actually failed to make it to orbit. NASA actually told us it was on an Earth-intersecting orbit. So it was fairly interesting. I had students that were undergrads that had spent their entire 4 years of their college career designing and building that satellite. It was an interesting day when we got to see it to fail to reach orbit. But we learned a lot in the process. The next one we launched was CXBM, Cosmic X-ray Background Nanosat here in bottom left. We launched in 2012 out of NASA Malphrus Flight Facility. Actually, I'm sorry, that was at Vandenberg Air Force Base. And I'll say a little bit about it when I talk about CXBM-2, which is a follow-on mission. But let me just mention the Pocket Cube project that Bob Twiggs has come up with. So the Pocket Cubes, you can see one being held by one of my students there, or the idea was that they were an eighth of a CubeSat, 5 by 5 by 5 centimeters. And in reality, we couldn't quite get to the 5 by 5 by 5 form factor, but this one is 5 by 5 by 20 centimeters. So it's still pushing the envelope. So somebody asked me earlier, what can you do with a form factor that small? And my response was, well, that's the same thing they asked Bob Twiggs and Gordy Puig-Soiree when they invented the CubeSat. So we don't really know. But we had the great fortune of launching 3 last year. And how do you get these Pocket Cubes on orbit was kind of an interesting story. So we have a relationship with the Gauss Group, which is a spin-off of the La Sapienza School at the University of Rome. And they have launch opportunities with the Russian Cosmotros on the Dnepr launch vehicles, fantastic vehicles. And so to be able to launch some of our satellites, we have built subsystems for the Italian satellites for EduSat and UniSat 5, and also built the orbital deployers in conjunction with the Gauss Group. In fact, we call them the Morehead Rome Femtosat orbital deployers, affectionately known as Mr. Bonds. So we built some of the subsystems and the deployers, and in exchange they allow us to launch some of Bob Twiggs' little tiny satellites, the Pocket Cube, so-called, of course, because you could literally fit one in your shirt pocket. So we were able to launch 3 of them in 2013. They were secondary payloads on the UniSat 5 mission. So UniSat 5 is a secondary payload on Dnepr. And it goes onto orbit, and after a few days, and then it deploys the Pocket Cubes. And the interesting thing is that they actually worked. I mean, when we ran the simulations, the budget, the mass, or the link budgets for the communications, it looked like we could barely close the link, the communications link. So we were able to close the communications link with all 3 with the big dish, and that worked pretty well. So then we tried with traditional amateur radio Yagi systems, and we were able to close the link on all 3 with the Aggies. We're actually able to close the link with a handheld radio once with one of the Pocket Cubes. So I think I've learned a thing or two about the numerical simulations that we've done. in the past, which don't always give you the, a very accurate measure of what to expect in reality. Generally, I thought it would be worse, but in this case, the Pocket Cube surprisingly performed extremely well. In fact, there's one that's still on orbit working right now after, well, it launched in December of 2013. So pretty incredible. So what's the killer app for the Pocket Cubes? We don't know yet, but Bob Twiggs, you know how he is. He'll come up with something, and they'll be an interesting form factor ultimately. Just a quick word about a project we're doing with the U.S. Space and Missile Defense Command called TechSat. It's a 3-unit CubeSat that hasn't flown yet, but it's of interest to me because with Honeywell Space and Defense Technologies, when they've been able to develop what's known as the DM processor, the Dependable Multiple Processor, and you can see it there on the bottom right. And it's actually a massively parallel supercomputer for the CubeSat form factor. In this case, it has 8 processors. They're off-the-shelf processors. Their GO6 modules are about $110 US each, so they're very inexpensive. But the idea there is to develop radiation-tolerant onboard processing systems for not much money. I mean, there's some fantastic radiation-hardened processors out there, but they're extraordinarily expensive and typically beyond the budget of most CubeSat developers. So the goal here was to develop a expandable computer system that was radiation tolerant owing to redundancy in the processors and also in redundancy and tolerance built in the software, the middleware specifically. So really the magic is in the middleware, where Honeywell wrote the software and we built up the hardware for the system. So we're actually, hopefully, we just got a contract with NASA Cases to fly the Dependable Multiple Processor on the NanoX external platform. So it should have space flight heritage within the next year or so. But for the remaining few minutes I'd like to talk about 2 missions that are my favorite ones, very briefly. And the first one is CXBN and CXBN2. Cosmic X-ray background nanosat, and the idea behind this 2-unit CubeSat is to increase the precision of the measurement of what's known as the cosmic X-ray background, the diffuse X-ray background. The diffuse X-ray background is essentially the integrated background noise of all of the active galactic nuclei in the early universe, and it's very difficult to make a good measurement of the diffuse background with a big spacecraft. In fact, this is one of the areas that small spacecraft, CubeSats in particular, can literally outperform big flagship, expensive spacecraft. And the goal is to try to increase the precision of the measurement so we can constrain the models. There are a couple of competing models that I won't go into, but the precision of the measurements currently do not allow us to choose between the various models in terms of an explanation of the underlying physics. So if we can get down to about a 2% measurement, then that will allow us to essentially figure out which of these models is correct. You can't really do it with this big spacecraft. And the reason is the error bars are in the current measurements, there are about 4 current measurements with large spacecraft, but the error bars are huge. And the problem is that when you're trying to make a measurement in the range of 30 to 50 kilo electron volts, you have to worry about cosmic ray protons. And the cosmic ray protons, when they interact with the high Z material in the spacecraft, of course they create interactions and daughter products. And the daughter particles can often be photons in the range that you're trying to measure. So with a big spacecraft made of a lot of high Z material, the measurements are necessarily contaminated by the presence of the material. However, if you make your spacecraft out of almost nothing, 2.4 kilograms of high Z material, then there's much less opportunity for contamination. And so it's really a better way to take certain measurements. So CXBN flew in 2013, and we didn't quite get the 2% measurement, but we got precise enough measurements that NASA allowed us to do a follow-on mission that we're going to launch in 2016. But the idea behind CXBN is that it was a sun-pointing spacecraft, and it had a CCT detector, and as it rotated, it essentially sweeps out the sky, a 36-degree field of view on the sky, and measures the X-ray background. Originally, we had used a CCT array that's a direct band gap semiconductor. It was a pretty good detector. It was a detector that was designed by a colleague of ours at UC Berkeley and built by a company in Colorado, but it was very expensive and very power hungry. In fact, the Solis detector we saw yesterday, probably a much superior detector than this one. It had good sensitivity, but it had some problems. So we were able to fly it and get flight heritage for it, but very expensive and it just didn't perform well. In fact, our colleague Garrett Jernigan had about a $1.1 million small business innovation grant and ended up with 4, so they were about $250,000 each. And really just didn't perform adequately to get the measurement that we needed. So we were looking for alternative sources, and what we've done is leverage technology from the medical imaging community. The medical imaging community uses CCT devices in nuclear magnetic resonance systems, and we found one that cost about $4,500 that works actually better than the experimental $250,000 detector. So this is what we're going to fly on the next flight of CXB and CXB2. And we're going to fly 2 of these detectors because they're relatively inexpensive and the power budget will allow us to fly 2 so we get better sensitivity. But there's an image of the detector and the initial data that we've taken with cadmium 109. So you can see that the spectrum is really pretty good and the sensitivity is excellent on these little detectors. Right now we're measuring an energy resolution of about 4 kilo electron volts. We hope to get down to about 2 keV, and we think we can with some improved electronics. So very excited about CXB2 and looking forward to flying it. We have to deliver it for NASA Lana launch in 2016, and it should fly in 2017. And again, would like to point out my collaborators on this mission, which are folks from the Keldysh Institute who've done the flight dynamical studies for us to help design the attitude determination control system. So it's been a really interesting program, and we're looking forward to that one flying. And finally, I would like to talk a little bit about an interesting mission that is a very high-risk mission, in my opinion, but has been an enormous amount of fun, called Lunar Flashlight. And this is a mission that's led by NASA JPL and Marshall Space Flight Center, and we fortunately have a role in the mission. Barbara Cohen is the PI at Marshall Space Flight Center, and there are other folks at JPL as well, and Morehead. But the idea behind this mission is to build a 6U spacecraft, CubeSat, that gets launched as a secondary payload on the Space Launch System's maiden voyage called EM1. Basically get a ride to the moon, and then once we get close to the moon, we unfold, believe it or not, an 84 square meter solar sail and use it for lunar capture, and then decelerate to get to a perilunar of only 20 kilometers above the south lunar pole, where we can search for water ice, essentially. So a little bit more detail. I understand now that there have been 3 missions selected, 3 CubeSats selected for the EM1 mission. Understand that there may be as many as 11 CubeSats selected on this mission. So it's to NASA's credit that they've allowed CubeSats to fly along on EM1. It's not going to have astronauts basically going to test the Orion spacecraft and the SLS system. But while you're there at the moon, why not drop a few CubeSats off and do some real science? And so it's to NASA's credit that they've accepted that challenge. So essentially what Lunar Flashlight does is it gets dropped off on the way to the moon. It does a lunar flyby, and it uses the solar sail to allow the moon to capture the spacecraft. But what's really interesting to me about this mission is the lunar capture trajectory. The orbital dynamicists at JPL have developed these crazy low energy capture trajectories. And essentially what they do is you use the gravity of the moon and the Earth and the solar sail together to spiral down in these, they look like spirograph I played with as a kid, in these complicated trajectories. Take something like 90 days to get into a spiral down trajectory. And then 247 revolutions to spiral down to the lunar periloom. As I looked through this and I tried to understand the orbital dynamics, it occurred to me one night, woke up in the middle of the night and I was asleep, and I thought, it's not really the solar sail that's the primary propulsion system. It's the Earth that's the primary propulsion system in these scenarios. And actually the sail is the perturbing system. So very complicated, but it makes these kind of lunar missions feasible with CubeSat form factor. So once we get to the periloom of 20 kilometers above the southern pole, then the 84 square kilometer sail, which is about the size of this, the floor space in this room, a little bit smaller, Then it becomes a reflector and reflects sunlight into permanently shadowed craters, deep well craters in the lunar southern hemisphere that have never received sunlight, where we think there's water ice. So the idea then is to reflect sunlight into these PSRs, these permanently shadowed regions, and look for water ice. And running a little bit short on time here, but I will just say a quick word or two about the technology. We'll look at the reflected sunlight with a 3-channel spectrometer that's tuned to some of the water molecule lines. And there's a picture of the complicated stow and deployment mechanism for the solar sail. It's amazing to me that you can squeeze an 84 square meter sail into a CubeSat. The science instrument has 4 parabolic telescopes, one for each channel, 3 or 4. It's not totally been designed yet, but again, it will look for water ice in the lunar southern hemisphere. So we've done some simulations in terms of the ground tracks that we can cover, and it looks like between 30 passes we can get great data. With 10 passes we can still get reasonably good data in the southern polar regions. So in summary, the lunar flashlight is a low-cost, under $10 million CubeSat method of locating significant ice deposits in the moon's permanently shadowed regions. And NASA's interest, of course, because it addresses a strategic knowledge gap in terms of the composition, quantity, and distribution of volatiles on the moon, their location, like water ice and hydrogen species. So cost-effective way to use CubeSats to do real lunar science. And then finally, I want to just say a quick word about the implications for mission ops. With EM1 going up, there are going to be 11 CubeSats going to the moon and the inner solar system, near Earth asteroids. With the LEO missions, the increasing in complexity, the science research data requires, to get to the ground, requires greater bandwidth, higher frequency. And so we have to think about the mission ops support. And so that's one thing that we've done at Morehead, is to develop a large aperture dish to support some of the inner solar system work with small satellites. When you have a CubeSat at lunar or near Earth asteroid that has 1.5 watts transmitter, at 300,000 or 400,000 kilometers out, the EIRP is extraordinarily low, and so you need high gain on the ground. And so we worked with NASA to develop the capability to have high gain on the ground to support these missions. And we do provide services for friends and colleagues, by the way. And I'll skip through because I'm running out of time here. But we've been fortunate to provide mission ops for a variety of different customers, for Planet Labs, for the ICE mission, which was kind of interesting. It was a satellite built in the 70s. It's still alive. We're taking data. We're tracking it about 34 million kilometers out. 11 science instruments are still working. Apparently, we really do have built satellites in the 70s, because the ICE is still functioning great. So, in conclusion, our ongoing and future missions, CXB and 2 were scheduled to launch in 2016. Lunar Flashlight will be on the EM1 mission, launch in 2017, maybe first quarter 2018. Looking forward to that. We have the DM processor flying on the NanoRacks external platform in 2016. A couple of other missions. Another really neat thing that we're trying to do with the Big Dish is to move toward deep space network compatibility. We see the communities in Europe and the US designing CubeSats, low-power CubeSats, that are going to really interesting destinations. And we're going to need a lot of gain on the ground and a lot of mission ops support. And then finally, we're always looking for new partnerships, and this is exactly the kind of venue where you network and you meet new people that have new technologies and have strengths that match your weaknesses. And so we anticipate a lot of new partnerships. Maybe some will come from this type of venue, which I have very much enjoyed. So in closing, I'd like to thank our supporters, NASA, JPL, Wallops Flight Facility, Marshall, Cosmotros, the Gauss Company, La Sapienza, and a variety of other partners. So thank you.
Thank you very much, Dr. Malphrus, for this very inspiring presentation. We maybe have time for one very quick question here in the back.
Hi. On the Lunar Flashlight mission, I'm kind of curious, I don't know how much you can say about attitude control and what's required with the sail, and presumably if you slew in, there's all stiffness issues with the sail. I don't know how much you can tell us, but I'd be interested.
It is a complicated project. I mean, it's basically a big tail wagging the dog, essentially. And reaction wheels, a combination of reaction wheels, possibly 4 reaction wheels as opposed to 3 to help drain the momentum. The sail to a certain extent can articulate a little bit to drain momentum, but it's going to be very interesting to problem to solve. The one good thing is that the sail doesn't have to change attitude tremendously. So the sail itself doesn't build up a lot of momentum, but it is a very complicated problem, particularly when we get to the transition between sail and the specular reflection capabilities of the sail. So interesting challenge. Folks at JPL are pretty good at that, so we have some level of confidence, although it's a high-risk mission, some level of confidence that it will work.
So thank you very much.
Thank you.